Okay. Well, thank you for letting me talk to you today. I am going to talk about the 30 years of the Hubble Space Telescope and kind of talk about its history initially. And then, of course, we can't have a talk about Hubble without showing some very pretty pictures at the end. So, but I just want to, one disclaimer is that I am not affiliated with the Hubble telescope or its affiliate institutions in any way. So this is just me talking as a fan of the telescope itself. So just it's been in space, I said, for 30 years, and we've gotten so much information and learned so much about the universe from this telescope, and it's really been a game changer to the field of astronomy. So I'm going to talk about some of its highlights and its history. So going all the way back to 1946, and Lyman Spitzer wrote a paper talking about the benefits of having a telescope in space. So this is even before we were having the space race, and before Apollo, we were already talking about having a telescope in space. But it wasn't until 1977 that the Hubble telescope, or the Great Observatory, received funding and construction began. In 1983, it was officially named the Hubble Space Telescope, and it was slated for launch in 1987. Well, of course, in 1986, disaster struck with the Challenger explosion, and that delayed all shuttle launches for the next several years. So it wasn't until 1990 that the telescope actually launched aboard the space shuttle, the Space Shuttle Mission 31 on Discovery on April 24th, 1990. The next day, Hubble was deployed out of the shuttle hatch, and there it is, the arm releasing Hubble, and it is now officially in orbit on its own. So the key mission of Hubble, or one of the key missions, was the discovery and determination, well, the determination of the Hubble constant. So what is the Hubble constant? Well, we have to go all the way back to 1908 and Henrietta Leavitt. And she discovered that there is a relationship between a certain variable star called a Cepheid and their intrinsic luminosity. She looked at these stars in the Large Magellanic Cloud, and since all of these stars were in the same galaxy, they were all the same distance from us, and which means any change in brightness that is seen is intrinsic to the star and not due to distance. Of course, if something gets further away, the fainter it's going to look. But if they're all the same distance, then if you see something fainter, it is intrinsically fainter. And she discovered that the longer of the period of variability, so the time it took to get from being bright to faint to getting bright again, was directly related to the intrinsic brightness of the star. So the longer the period, the brighter the star intrinsically was. So now if you know how bright the star is, I know I have a 100-watt light bulb, say, and I can measure how bright that light bulb appears to be, I can now calculate its distance. And so this is the first real distance measurement we had to some distant galaxies. Fast forward to 1912, and we have Dr. Slipher, who became the director of Lowell Observatory, started taking spectra of some of these nearby and a few distant galaxies. And he discovered that there was a Doppler shift to these galaxies and determined that most galaxies were redshifted moving away from us. So what is this Doppler shift? Well, so if we measure the light, the spectral light coming from a galaxy, if the spectral light is redder than it should be, it means it's redshifted and that galaxy is moving away from us. If that galaxy light is bluer than it should be, then it's blue shifted and that galaxy is moving away from us, or moving towards us. It's that same effect that you get from an ambulance siren. It has a higher frequency moving towards you and a lower frequency moving away from you. The same thing happens with light. Slipher discovered that most of the galaxies were redshifted. This was a paradigm shift because it was thought that galaxies should be moving in random motions. Half should be blue shifted, half should be red shifted. But instead, he found that almost all of the galaxies that he observed were red shifted. And furthermore, the larger the redshift, the faster the velocity is away from us. So the more red it looks, the faster the galaxy is moving away. So putting the Leavitt law and our Doppler shift together was Edwin Hubble in 1924 at the 100-inch Mount Wilson telescope. And he measured the Cepheid variable stars in several galaxies out to fairly far distances and used the Leavitt law to determine those distances. And this was the first time we actually had the idea of a galaxy. In 1920, there was a great debate as to whether these spiral nebulae, so they were called the Great Andromeda Spiral Nebula, was actually a galaxy unto itself, like the Milky Way, or the Milky Way was the entirety of the universe, and these spiral nebulae were just a part of our own galaxy. So thanks to Hubble and using the Leavitt law to find these distances, he realized that these galaxies, now called galaxies, were much, much farther away than the believed at the time size of the Milky Way by orders of magnitude. They could not possibly be a part of the Milky Way. These are galaxies unto themselves. And our knowledge about how large the universe is increased significantly through this work. He also measured the spectra of these galaxies and discovered that there was a relationship between the redshift and the distance. The further away a galaxy was, the higher the redshift was, which means it was moving faster from us. So the further away the galaxy was, the faster the velocity away from us. And this became known as Hubble's law. This also said that the universe was expanding. We no longer had a steady state universe. Einstein thought the universe was a steady state, static, not moving. This showed that not only do we not have a static state, but the universe is in fact expanding as all of these galaxies are moving away from us. So this gave us the Hubble constant. What is the slope of this? So this became a very powerful tool in measuring distance, because you can always take the spectrum of a galaxy and determine the redshift and figure out how fast that galaxy is moving away from you. But you can always see a variable star in a very far away galaxy. If the star is too far away, you can't pick out individual stars anymore. So you can't figure out the distance, or you have to use a different method of finding distance. But if you know the Hubble constant and you know the velocity, you can calculate what the distance to that galaxy is. So this became a very powerful tool in figuring out the size of the universe. But then, of course, with science, we discover something new, and there's so many more questions that resolve. So what is the actual value of Hubble's constant? Well, Hubble himself thought it was 500, and the units of this are kilometers per second per megaparsec. A megaparsec is 1 million parsecs. So in Hubble's time, he thought that if you went 1 million parsecs away from our position, the galaxy at that distance should be moving away from us at 500 kilometers per second. If you went out to 2 megaparsecs, it would be moving 1,000 kilometers per second away from us. Hubble had some issues. He didn't know about different populations of stars, so the Leavitt law did actually need a recalibration later. And he also thought he was looking at individual stars when he was actually looking at some clusters in the very far away galaxies. So that threw off his calibration. If we go ahead to the 1970s, there were two camps. One said it was 100 and one said it was 50. Very prominent astronomers in both camps. And if you were a hapless young astronomer starting your career in the 70s and 80s, you had to pick one. And if you picked 100 for your calculation values, then everybody in the camp of 50 didn't believe anything you were saying. And if you picked 50, no one in the camp of 100 believed anything you were saying. And if you picked 75, no one listened to you, would listen to you at all. So you had to pick one. And this was a great debate for a long time as to what the value actually was. So to solve this, we of course have the Hubble Space Telescope. That was its primary mission, was to get accurate distances to these galaxies from the Cepheid variables. Because it is a 2.4 meter mirror in space. Now we can see these individual stars in galaxies that are very far away, so we can get distances accurately to very far away galaxies and observe the spectra of these galaxies. So we can get the accurate redshifts and velocities and then calculate what the Hubble constant is. So what is the answer? Is it 50? Is it 100? Turns out it is actually 75, right in between. It's 70 to 75, and that it's been that way for several years now, and that seems to be the right answer from Hubble. I will say there is one mystery we currently have in the field, and that is if you measure the distance in redshift to the cosmic microwave background instead of nearby galaxies, you get a value of 67. And the value of 67 and the value of 70 to 75 are not within the error bars of each other. So there is a discrepancy in these two values that is still a mystery that is being worked on today. So the first light image of Hubble, it was a star cluster and tried to focus on these stars. And in May 1990, right away, people knew there was a problem. These stars were supposed to be just a few pixels big, sharp, crisp points of light, and instead they're blurry. We have this very distorted, distended image of these stars. And so the question is, what went wrong? There was a lot of moving of the secondary mirror, trying different things, trying to get these stars in focus, and none of that worked. They finally realized that the calibration on the primary mirror when the glass was ground was off, and it was off by all of 2 microns. Now the width of a human hair is about 50 microns, so the mirror was only off by 2 microns, but it was enough to cause this blurriness. So when the light hit the mirror, you ended up with what we have in kind of figure A here, where all the points of light, the rays of light, are not coming to a single focus. They're all focusing in a different spot versus all focusing together and making a nice crisp focus. So how do we fix this? Well, there were 2 actual corrections. There was already a camera on Hubble called the Wide Field Planetary Camera, and they had a backup, and they had planned to do some upgrades to that camera anyway. And so the Wide Field Planetary Camera 2, or WIFPIC 2, was installed in Hubble. And that itself had some internal corrections for this blurriness. But that didn't correct the rest of the instruments, the spectrographs, all the other instruments that were on Hubble. And so the correction for that came in CoStar. And that's here's CoStar right here. So it's all of these arms have these pick-off mirrors, and all of these mirrors have different curvatures to them. So as the blurry light comes into from the telescope, from the primary mirror, it will hit these pick-off mirrors, and it will be corrected by the curvature of those mirrors and then sent into the various instruments that are needed. So that was the correction. CoStar is essentially a pair of glasses for Hubble, and it really corrected the problem. So here's this bright star I showed before where it was all blurry, and then there it is in sharp focus. And then, of course, M101, very blurry image. You can't see really individual stars. And now, after CoStar, you can see the glorious spiral M101 and all of its glory. So, but that didn't happen until 1993. So we had 3 years of blurry Hubble images. But of course, since CoStar, Hubble has worked beautifully, even after several service missions and instrument changes, and Hubble is still going strong today. So now for the pretty pictures, and of course I can't give a Hubble talk without showing a bunch of pretty pictures. But I didn't want to show the classic pretty pictures that everyone is familiar with Hubble. You know, there's the Crab Nebula behind me, the Whirlpool Galaxy. You may have posters of these or bookmarks. You see them at trade shows. So I didn't want to show all of those because everyone has seen those before. So I wanted to give the deep cut edition for Hubble and highlight some images maybe you're not so familiar with, and talk about some of the Hubble discoveries. So this is the 30th anniversary, but back at the 25th anniversary, this image was released, and I liked it just because it was pretty. This is a star cluster, a star forming region. I'm going to show a couple of these going forward. It's about 1 million years old. It's called Westerlund 2. You see all of these blue stars, very hot, bright blue stars, very young. So all of these stars formed just within the last 1,000,000 years, if not a few 100,000 years ago. So very young stars, large star forming region. And it's just really pretty. Planets, the ubiquitous planet shots. Couple of highlights. Very detailed picture of Mars when it was at its closest approach in 2007. So Mars gets very close to the Earth every 2 years, but it just happened in 2007. The alignment was just right that it was even closer than usual for its usual 2-year close approach. So you're able to get great detail of Mars. You can see the polar caps, just really pretty. And then just a few weeks ago, Saturn has gone into summer in its northern hemisphere, and Hubble took a picture, very nice picture of Saturn. You can see some storms on the surface. And then Jupiter, this is a UV image, so ultraviolet image of Jupiter. You see a lot of the storms of Jupiter. And you can even see some detail on the moon of Io. There's some color contrast there. You can see some of the volcanoes on the surface of Io, and of course Io's shadow on the surface of Jupiter. So I said there's some more star-forming regions. So these are very large dust clouds, molecular hydrogen gas clouds. And within the middle of these clouds, you have a gravitational collapse in an overdense region. And that collapses and collapses and collapses. It raises the density, it raises the temperature of that gas to the point where nuclear reactions start and you have the birth of a star. So within these very dark clouds, you have stars, very young stars being born. So there's a couple of bright ones in the Cone Nebula. You can see some glow at the tip of this from these stars that are just being born in the Trifid detail. And of course, the Orion Nebula over here, classic Hubble image, and then the detail of within the Orion of the Horsehead Nebula itself. Very classic Hubble image there. But it's hard to see the stars if you're looking in visible light because you have all this dark dust in the way. And the way to get around that is to look in the infrared. So here is the visible image of the Eagle Nebula, classic Pillars of Creation Hubble image here. But if you then instead look in the infrared, that dust cloud almost disappears. And suddenly you can see all of those stars that are being formed within that dust cloud. So all of these little red dots are brand new stars that were just formed not that long ago. And if we could zoom in on some of these stars, what you would see are these protostars with protoplanetary disks. And so buried within these little clouds here are these bright protostars that just formed. And this cloud is actually a disk that is in orbit around that star. So this is a baby solar system. You have a star that has just turned on, and then the debris that's left over from the creation of that star is now in orbit around the star. And that debris cloud, that disk, can have overdense regions where you can start forming planets. So we think this is how Jupiter formed, how Saturn formed in our early solar system. So there could be active planet formation going on right now within these disks that we're seeing edge on with the star buried in the middle. Some more molecular clouds. This is an example of some massive star formation. So all of these bright blue hot stars, very, very massive stars. This is the Tarantula Nebula and its associate star cluster in the Large Magellanic Cloud. I show this one because right in the middle of the star cluster is the most massive star we are currently aware of. And by massive, I mean 315 times the mass of the sun. So when I say massive stars, I mean massive stars. All of these bright blue stars are being born within this molecular cloud. And here's another example of the Carina Nebula. Very pretty. There's all sorts of things annotated here, but I wanted to highlight Eta Car in particular, which is one of my favorite massive stars. So that sits right here in the Carina Nebula, and the detail of it is over here. Now it's a binary system, which gives it this kind of double lobe outflow effect. So when you have massive stars like this that are 30, 40, 100, 300 times the mass of the sun, they have very strong stellar winds. So the star itself is outflowing its outer atmosphere out into space. And so that's what we're seeing here with Eta Car. This is not actually, these little clouds around the star, which is buried right in the center, is not part of the entire Carina Nebula. It's actually an outflow from the star itself. These really massive stars are commonly called Wolf-Rayet stars. And we see a lot of these with these clouds. So there's the star in this case, right down here in the center. And this entire cloud around it is not a star-forming nebula. It's actually the stellar wind that's been outflowed from the surface of the star to create this cloud. And here's another one. This complex is called the cosmic reef. And so this red nebula is actually a star-forming region, but this blue nebula down here has a Wolf-Rayet in the middle of it. And the entire blue nebula is from this outflowing wind. So you have this big molecular cloud forming stars, and then you have this Wolf-Rayet making its own little cloud from this outflowing stellar wind. And then eventually, these very massive stars die catastrophically when the nuclear reactions slow down, they run out, the core collapses, and the rebounding shockwave blows the entire star apart. The most recent nearby one was 1987A in the Large Magellanic Cloud. And 87A is interesting because before it exploded, the star released a lot of energy, or released a kind of a cloud. It's not a Wolf-Rayet. It's not massive enough to be a Wolf-Rayet, but massive enough to explode. So it doesn't produce these big nebulous cloud around the star, but it still has an outflow from its surface. But it didn't have a symmetrical cloud. It released a ring of debris. And so you had this ring of debris sitting around the star when it exploded. And so you see a time evolution of this, where in the middle, you have this hot debris from the explosion with this dust ring sitting around where the star was. But then as the shock waves of the explosion expanded out into space, it eventually ran into this dust ring, heating it and lighting it up. So you can see over time exactly where the shock wave of that explosion is and how long it took to get out to that dust ring. And then there's another type of supernova called a type 1A, which is, instead of a massive star dying catastrophically, it's actually from a white dwarf. And a white dwarf has a limit to its upper mass. It's actually 1.35 solar masses. And if it goes above that mass for whatever reason, it could have merged with another star, it could have accreted material from another star, a binary companion. There's several ways it could actually get too massive. And if it does, it becomes unstable, and the white dwarf then detonates. And these are very bright supernova. Here's an example of one going off, this dot in this galaxy. 1984, supernova 1984D was a type 1A. You can see how bright they are compared to the rest of the parent galaxy. And these are very helpful for getting distances as well, because as a white dwarf, most white dwarfs explode at the same mass, therefore they have more or less the same intrinsic luminosity. So here's another case where we know the intrinsic luminosity, we can measure its apparent brightness, and if we have those two things, we can calculate the distance. So we can find out how far away these galaxies are if a type 1A supernova goes off in the galaxy. So these are called standard candles for that reason. And then after the explosion happens, we're left with a debris field that's a supernova remnant. So here's a couple that were from a massive star. The Veil Nebula is a very classic image. There are several. The Veil Nebula is so large that Hubble can't observe the whole thing. The entire Veil Nebula is actually larger than the moon in the sky, the full moon in the sky. It's extremely faint, but it is quite huge. And pieces of it are absolutely gorgeous. And then we have this one that I thought was just kind of pretty, N63A. So this is a very messy explosion that happened from a exploding massive star. And then the kind of red bubbles are from white dwarfs. So these remnants have neutron stars in the middle of them. The core of that massive star is still left over and hanging around within the middle of these nebula. But when a white dwarf explodes, there's nothing left. It's just completely obliterates itself. But then you're left with these kind of bubbles. That is the remnant debris of that explosion. So when you have a star that isn't massive enough to explode, something like our sun will not explode, but it will poof off its outer envelope and form a planetary nebula. And there are very many versions of this, and they're all quite beautiful. At the middle of these, so these are kind of an example of several quote-unquote roundish ones, somewhat symmetric. There's a white dwarf at the middle of these, and that is the core of what was a sun-like star. And then the outer atmosphere of that star is now receding out into space. So it's not a catastrophic explosion, but it still forms these very pretty nebula around what was the core of the star. So here's some examples. They're called planetary nebula, even though they have nothing to do with planets, because one of the first that was observed was the Ring Nebula, the Northern Hemisphere Ring Nebula, which is not this one. This is in the Southern Hemisphere, but very similar to the Northern Hemisphere Ring Nebula. And in the early telescopes, it looked a lot like Saturn. So there was this idea of, oh, well, it looks like Saturn, and it's kind of fuzzy, so we'll call it a planetary nebula, without knowing at the time what was causing such an event to happen. So now that we know it is actually the remnant death of a sun-like star and has nothing to do with planets, but we're stuck with the name. So these are all planetary nebula. They don't have to be kind of symmetrically round. They can also be bipolar. And so here's some very pretty examples of some bipolar planetary nebula. You can still see there's a white dwarf in the middle of these. But instead of releasing its atmosphere and releasing its contents symmetrically, it's released along a preferential axis. And I thought this one was kind of interesting, this 13208. This is kind of a proto-planetary nebula. It's just started to release its mass out into space. So it's not quite a planetary yet, but in very short order, it will end up looking like these bipolar ones. So this is kind of rare to catch something in this kind of early proto-planetary nebula state. They're not in this regime of their evolution for very long at all. So we don't see too many of them. And then moving out into galaxies, of course, spiral galaxies are ubiquitously beautiful. But I wanted to highlight just a couple of them here, other than a couple that are just super pretty. But the two I wanted to highlight were with these asterisks, NGC 3972, this lovely spiral in Ursa Major, and NGC 5584, which is this lovely face-on spiral in Virgo. Both of these were actually very important to Hubble's mission of determining the Hubble constant, and important to calibrating our distances. So both of these galaxies have many, many Cepheid variables in them. And when you have that many stars in the same galaxy, they are at the same distance. Of course, the galaxy does have some thickness to it, but the thickness of a galaxy, particularly a spiral galaxy, compared to the distance away from us, is within the noise and fairly negligible. So you can assume that all of the Cepheids are at the same distance if they're in the same galaxy. So that gave us a nice calibration distance to these two galaxies. And then we were fortunate enough to see a type 1a supernova go off in each of these galaxies. So the Cepheids we can see if we can see individual stars within a galaxy, we can get a distance. But if it's a very, very far away galaxy, we can't see individual stars anymore, but we can see type 1a supernova and measure the distance that way. So we have a close distance and a far distance measurement, but we need a way to calibrate against the two. And so these two galaxies help us do that because they have both Cepheids and they had a type 1a go off. So we had this kind of linking between the close measurement and the further away measurement. I also want to highlight that 5584 was actually discovered in 1881 on a fairly small telescope by E. Barnard of Barnard star fame, if you're aware of Barnard star. And so this is potentially a good telescope and camera observing galaxy to go after if you're into that sort of thing. So I kind of wanted to highlight that because it's a very, very pretty face-on fluffy spiral. Just a couple of notes on galactic collisions. We see this quite often, where you have two galaxies running into each other. In the case of ARP 272, these two galaxies are actually spiraling in opposite directions, but they're running into each other quite violently. And then in ARP 148, you have this kind of edge-on galaxy that completely bullseyed a more face-on galaxy and just ran right through the middle of it, completely disrupting it. So these can be quite violent, and eventually these galaxies will collide, not only collide, but merge and form one larger galaxy. And we can see evidence of mergers within the evolutionary history of ones that have been collisions and have been mergers. An example of one that's had several mergers is this NGC 1132. It's an elliptical galaxy, so this kind of football shape. This one's actually called a fossil elliptical because it's called red and dead. It has only old stars. It's very red. No blue massive stars anymore. They've all died out, not forming any new stars at all. But it is quite large, and its multiple galaxies have collided together to form this particular elliptical galaxy. And then on the very opposite end of the spectrum is M61, which is a starburst galaxy. So this one has only red and old stars. And this one has several blue, hot, massive stars currently being formed. So many, many regions of where there's these molecular clouds actively forming stars at a very rapid rate. So our own Milky Way is still forming stars, but when you have a starburst galaxy, the rate of formation of stars is significantly higher than a typical galaxy like the Milky Way. So many blue stars in this one. And then I wanted to also highlight a type of galaxy maybe you haven't heard of. It's called a lenticular galaxy. And so this is an example of one. It has this kind of elliptical halo shape with a very bright core. So that part of it looks very similar to this elliptical galaxy. But you also see these dust lanes and kind of hints of spiral arms. And so it also has some spiral structure. So a lenticular galaxy isn't sure what it is. It's both a spiral and an elliptical at the same time. So it doesn't want to be classified as one or the other. It's actually both. And I can't talk about Hubble without talking about its deep field. So the very initial deep field was done in 1995. And it looked at a quote-unquote blank piece of sky. So there was nothing there as far as anybody could tell. And Hubble just stared at that spot for 10 days. It was off in Ursa Major. And lo and behold, we saw more galaxies at much farther distances than we ever thought was going to be possible. There were fully formed galaxies much further away, and therefore much earlier in the age of the universe than we thought galaxies would form. And so the universe evolutionary history took a paradigm shift in realizing that there were there were galaxies forming very early on in the universe's history. Because of the success of this, we went from the deep field to the ultra deep field. This was done over 11 days, over the course of several months. And we saw about 10,000 galaxies in this image. There's only, I think, 4 stars in this image. So anytime you see something that has a diffraction spike like these, that's a foreground star in the Milky Way. Everything else, even these tiny little dots, are distant galaxies. Every single dot is a galaxy. And just the idea that there's so many galaxies out there, far more than I think we realized. This is kind of a game changer. So just as Hubble back in 1924 expanded our knowledge of the size of the universe, I think the ultra deep field also expanded our knowledge of the size of the universe. And then, not to be outdone, so we have the deep field, we have the ultra deep field. Now we also have the extreme deep field. This was done over 23 days, over the span of 10 years. So 23 days of exposure time over 10 years. This was released in 2012. And the couple of interesting things in really pushing the limits of Hubble, how far back in time, because the further back we look, the further back in time we're looking, how far back can we really look? And lo and behold, the oldest galaxy is just over 13 billion years old in this image. So that's only 450 million years after the Big Bang happened. So it was kind of a surprise that galaxies could form that soon. And be fully formed. This isn't like proto-galaxies. They're actually normal galaxies that are that old and that far away. Also of interest is the furthest known away red dwarf star, which is that little guy right there. Most red dwarfs that we see are only tens of light years away, because red dwarfs are smaller than the sun, which means they're intrinsically fainter. And so we can't really see them really far away from us. But thanks to the extreme deep field, this one is actually 59,000 light years away compared to the ones we typically view as being 30, 50 light years away. So really, really far away, red dwarf in this image. So I just want to conclude with a couple of recent discoveries from Hubble. Hubble is still going strong, as I said, in being 30 years old, and there's a lot to still be learned with Hubble. Big news is the discovery of this structure, known as the bat. You can see it has kind of wings coming out here. So this is a molecular cloud. This is a star-forming region, and there's a new proto-star in the middle of this bright region here. So that's the bright star. But it has a disk around it. So if you remember those proto-stars with those planet-forming disks shielding the star and blocking it out. This star has that same thing going on, but the star is bright enough that it's actually causing a shadow across the disk, and we can see the shadow of the disk spread across the rest of the molecular cloud. So just like a lampshade around a bright light bulb, we're seeing the shadow against the rest of the molecular cloud here, spread out from either side. And the cool thing about this is that we've taken, or Hubble has taken images of this structure over a year, over the span of 404 days. And you can actually see the shadow move. It's not static. And so that tells us that this disk that's around the star is not just a flat pancake disk, it's actually warped. And so as the disk rotates around the star, we're seeing different aspects in shadow. And so that's causing this flapping motion. So the bat is flying, but we're seeing the warping of the disk and how the shadow changes. A second discovery is from the Sombrero galaxy. And so the Sombrero, of course, is this beautiful edge-on spiral galaxy. M104, and classic Hubble image of the sombrero. But the sombrero itself is a little strange. Galaxies that are spirals like the Milky Way have what are called halos around them. So there's this bright, distended region above and below the plane of the disk. And these are full of very old, very red, typically metal poor stars. So they're pretty ubiquitous to spiral galaxies. With sombrero, its halo is significantly larger than what would be typical for a spiral of its size. And the halo doesn't just have red old stars, it actually has young stars within the halo, which you don't see in a typical spiral galaxy. And the halo is quite extended, even beyond what you see here in this kind of fuzziness. It actually extends really far out, and some of these young stars are highlighted in these inset images. So why does this sombrero have this huge halo with young stars? One possibility is that it merged with another galaxy. And so as the galaxy came in, the young stars that were in that galaxy got thrown into some chaotic orbits, got thrown high above the plane of sombrero, and formed this very large halo. So it's a cannibalized galaxy that sombrero ate. And now we have these extended young population around the sombrero itself. But problem with that is that if you remember the galaxy collision images I showed, they're quite catastrophic, and the structure of the galaxy, even if it's a much larger galaxy with a smaller one running into it, the structure of that galaxy gets disrupted, and so it doesn't keep its nice, pretty spiral shape. Sombrero has. Sombrero looks like a galaxy that's been sitting by itself for billions of years without anything interacting with it. So this is a mystery. We don't have an answer to this question yet as to how you can get young stars in a very large halo around in this galaxy. And then lastly, star formation, as I've been harping on, not only galaxies forming early, but star formation happened very early in the universe. This is an image of a galaxy cluster, and it's the cluster galaxies, so these bright things, are gravitationally lensing very far away galaxies behind it. So all of these arcs that you see around the main galaxies are actually galaxies unto themselves, but very, very far away behind the galaxy cluster, but in the same line of sight. And because this cluster is acting like our own telescope, it's a lens. It's called gravitational lensing. And just like an optical lens, it's magnifying the light from those background galaxies. So normally those galaxies would be too far away for us to see, but because this cluster is acting like a magnifying glass, we can now see those galaxies behind it. And those galaxies are very old. They are 500 million to 1 billion years old in the terms of the age of the universe when they formed. And they're fully formed. And furthermore, they have completely normal stars in them. We don't see any initial population of stars. So the very first stars that formed in the universe, we think only had hydrogen and helium in them. They didn't have all of the quote-unquote metals. So the carbon, the oxygen. The sun has over 70 identified elements in it. Just after the Big Bang, there was only hydrogen and helium in the universe. And so the first stars could only be made of hydrogen and helium. They're known as POP3 stars. And so the idea is, well, if we can look at these galaxies really far away, those galaxies, we're looking back in time, should only have hydrogen and helium. And these galaxies look completely like normal galaxies. They don't look like very young galaxies. So we don't know yet when the very first galaxies happened, when the very first stars started forming. But by the time the universe was 500 million years old, they had already formed. So the hunt continues. So in the conclusion, Hubble is still going strong, and there's plans that it should be fine and healthy well into the 2030s, and we're going to have a lot more information coming from Hubble, I think, in the next several decades. So if you want to look at more pretty pictures or get more information, Hubble site is a great resource for pictures. That's where I pulled most of mine from. Or the spacetelescope.org itself. And if you want to see what Hubble is looking at in real time, there is Space Telescope Live. And it will tell you what object Hubble is looking at and who requested the time for Hubble. So thank you very much, and I will take questions.